Hey guys, so we're back to Earth structure here, which we said uh, is layered, right? It's stratified, and based on the early formation of the Earth and the molten material, the heavy material migrated towards the core while the lighter material surfaced at the crust. I want to focus on the crust today. After all, that's where we live. There are some pretty amazing processes that help to reshape Earth's crust, and that's what we're going to be exploring within this unit. So let's talk about the basic building blocks of the crust, which are minerals. So what is a mineral? Minerals occur naturally in our crust. They tend to be solid. All minerals are inorganic. And that's actually pretty important because we know minerals are all rocks, but it turns out not all rocks are minerals because some rocks contain organic material, whether it's derived from plant material, skeletal remains, or shells, and so forth. So minerals, in order to be classified as a mineral, it's inorganic. Minerals actually have a definite chemical composition. So for example, graphite is made of carbon, diamonds are made of carbon. Despite the fact that they're made of the same stuff, they are very different from each other, right? So it's all about how those atoms are arranged, and that orderly pattern is what determines characteristics. For example, graphite's super soft, you can write with it. Diamonds are the hardest mineral on planet Earth, so they do vary and have different characteristics. So we're going to move into rocks now, and rocks basically are minerals, but sometimes they have some added bonus features, some additional constituents to them. This is geology, and I get it, like not everyone is going to be completely blown away by rocks, especially when you're in the classroom. A rock on your desk is not that interesting. But I highly encourage you, if you ever have an opportunity to take a geology class, a field geology class, it's an incredible experience because that's where these rocks come to life, where you can actually see how they provide evidence for Earth's history and what's actually happened. So let's take a look at rocks. What is a rock? There's a big question for you guys. A rock is a mineral, one or more mineral bound together, right? And we have two major varieties of rocks, and these include monomineralic, so a rock composed of one mineral. So limestone is made of calcite. Remember that bubbles with acid through dissolution as carbonic acid dissolves it, releasing carbon dioxide. Quartzite is comprised of quartz. So most rocks on planet Earth, however, share a variety of minerals. So granite, some of you may have countertops at home, and you can visibly see how granite is crystalline with a variety of minerals, right? So you got the white quartz, maybe some pink feldspars, black micas. So lots of minerals bound up into one rock. When we look at rocks, we actually break them into three categories, and we're going to have a screencast on each rock type. The first one here is igneous rocks. Igneous rocks are formed from the cooling and solidification of lava and or magma. Sedimentary rocks come from broken pieces of rocks that are compacted and cemented together, and metamorphic rocks are derived from heat and pressure. So it's all about how they formed, the processes, the environment in which they form is what distinguishes one rock type from another. Today we're going to start with igneous, and the reason we're starting with igneous is because the majority of rocks on planet Earth are in fact igneous. You only have to think of how the Earth formed. It cooled, right? It was molten, and therefore the bulk of Earth's crust is igneous in origin. It's from the cooling and solidification of lava or magma. So that begs the question, well, how does magma and lava differ? It's the same molten material, it's just location, location, location. In other words, magma is that hot molten material that cools inside the Earth. If that same material exits the Earth in a volcano, for example, then it becomes lava. And so this affects their cooling rate. And so therefore, we're going to get both intrusive rocks, those that form from magma inside the Earth, and extrusive igneous rocks, those that form from lava, which cool quickly outside of the Earth. The intrusive varieties are again derived from magma. So sometimes that hot material doesn't reach Earth's surface. It goes off into these lateral sills and dikes where it fills these cavities and it cools. Now, since it's cooling inside the Earth, it's cooling under high temperatures and high pressures. That means the cooling process is quite slow. So as it cools and solidifies, the crystals that solidify and form get very large. The longer it takes to cool, the larger the crystals grow. And these rocks tend to have large intergrown crystals as a result. So here, for example, is a piece of granite where you can actually see, without a hand lens, large crystals intergrowing together. Slim is a great way to get to know this. S, if you would like to write that down, could stand for slow, as in slow cooling. L could stand for large, as in large intergrown crystals. Since the magma cooled slowly over time, it solidified and the crystals got very large. I could stand for intrusive, or rocks that form in the ground or in the crust. And M would stand for magma, as that's the molten material below Earth's surface. Extrusive rocks are very different. These form from lava, where that magma within the Earth reaches Earth's surface and is jettisoned or propelled outside of the Earth by a volcanic cone or perhaps a fissure in the Earth. That material is now exiting the Earth, and we then call it lava. Well, what happens when it reaches the atmosphere? There's a reduction in temperature. There's a reduction in pressure that allows the lava to cool very quickly. This rapid cooling does not allow development of crystals, or at least the crystals can't grow very large. Sometimes the lava cools on contact with the atmosphere, in which no crystals develop at all. This can produce some beautiful rocks. This is called obsidian, and this produces a glassy texture where you do not see a crystal structure to it whatsoever. Another texture that's common to extrusive igneous rocks are a vesicular texture. That lava that exited the Earth contains gas. That gas is free to escape the lava when pressure is reduced. It bubbles, and that escaping gas then produces rounded gas pockets as the lava cools and solidifies into stone. So this creates sort of pocked marks or holes or a porous rock. And this is, of course, lava rock, or this is actually known as scoria. And it's quite difficult to walk on because it doesn't feel good. That's it for today, or actually that's it for igneous rocks. You guys are going to move on to sedimentary and metamorphic rocks next.